So the other day, we talked about the different types of energy. We talked about chemical energy, nuclear energy, kinetic, potential, mechanical, all those kinds of things. So we know kind of the types of energy. Today we need to look at how does energy move? How can we harness energy, make it do work, things like that. Okay, the movement or change of energy is known as thermodynamics. Thermo means energy, dynamics means to change, right? So thermodynamics means when energy changes or moves, okay, within a system or something like that. Okay, so all machines that we use are governed by certain physical laws, right? The laws of thermodynamics in particular. So these govern kind of how energy moves around. And specifically today, we'll look at heat and a little bit about mechanical energy, mostly heat today. Okay, so things we need to know. First off, there's different kinds of systems, okay? Because energy moves in systems. Most systems that we would encounter in the real world are what we call open systems. An open system can exchange both matter as well as energy with its environment. Okay, so you and I would be considered open systems, right? Because in the wintertime, you might have noticed it was kind of always cold in here. That's because I allowed you guys to heat the room because I understand how thermodynamics works. Your body temperature is 37 degrees Celsius. And because you're warmer than the air in the room, you'll make the air in the room warmer. Okay? Doing this for a long time. Okay? Usually, by the end of the day, usually by the time you guys get in here in period 4, the room is about 3 to 4 degrees warmer than it is in period 1. Okay? Just because people have come in. And they're an open system. They're exchanging energy with their surroundings. The surroundings would be the air in the room, okay? Things like that. While you're also in here, you're exchanging matter with your environment. You're breathing in and breathing out, okay? So you're exchanging oxygen for carbon dioxide, okay? All of that kind of stuff as we breathe, okay? So you're not only exchanging energy, you're also exchanging matter. So you're an open system. Everybody all right with that? Okay. Okay, a closed system, okay, is one in which only energy is exchanged. It's airtight. No matter is exchanged at all. So if I had gone to the grocery store and bought like enough steaks to last me for 2 months, and I would want to put some of them in the freezer, right? So I would put them in a Ziploc bag to make sure that no matter is exchanged. Okay, once I seal it in there, nothing gets in or out except energy, because once I throw it in the freezer, it's going to lose energy to its surroundings, okay, and eventually freeze. Okay, everybody all right with that? All right, and the last one is kind of a theoretical construct. It doesn't really exist anywhere, and that would be an isolated system. Okay, this doesn't exchange matter or energy with its surroundings. Okay, it's nearly impossible to do this. Right? It's quite easy to build a closed system where no matter is exchanged, but it's nearly impossible to perfectly insulate something against any energy loss. Right? We've built pretty good insulators. Okay, they can retain energy for a long period of time, but they're always slowly going to give energy away. Okay, everyone kind of follow me there. All right, so those are the 3 kinds of systems. Okay, we need to know what they are. Yes. Yeah. It wouldn't ever lose any energy. So like a perpetual motion machine would essentially be an isolated system. And we can't build those because everything slowly bleeds energy away. Right? All right. So a couple of definitions here. First off, what's a system? A system is a set of interconnected parts. So an engine is a system. Okay, you're a system. You're a bunch of interconnected parts, right? And the 3 kinds of systems. An open system exchanges both. Whoa. Hang on. Okay, so an open system, okay, is there we go, is one that exchanges matter and energy with its surroundings. Okay, a closed system cannot exchange matter, but can exchange energy with its surroundings, and an isolated system doesn't exchange either one. Okay. Okay, there's essentially 2 laws of thermodynamics that we need to be concerned with. The first law is concerned with where energy comes from, what happens to it, okay, when things happen, when work is done, etc. And the second one is concerned with how does energy move. Okay, so one is concerned with its use and conversion. Okay, the other is concerned with its movement. So the first law of thermodynamics is essentially the law of conservation of energy. That is, that energy can't be created and it can't be destroyed. Right? Energy is always there. And that's something that sometimes people have trouble understanding because they can envision energy being created, right? Like when I burn wood in a campfire, I'm making heat. Am I actually creating energy? No, I'm just converting one form of energy to another. There was stored chemical energy in the wood. And when I start it on fire, the reaction with oxygen releases or converts that stored chemical energy into heat. So I'm not creating energy, I'm just turning it from one form to another. Okay? Photosynthesis, same idea. We're harnessing energy from the sun and making chemical energy. Okay? So it's essentially important to understand that, again, energy can't be created or destroyed. It's also important to understand the difference between heat and work. Heat and work are both transfers of energy. And I think I said this the first day too. Okay? Heat and work are both transfers of energy. Okay? Work is a transfer of mechanical energy. And so as a result, involves the movement of matter from one location to another. Whereas heat is a transfer of thermal energy from one location to another. Okay? So we can write it like this. Shorthand here. Work is a change in, so delta means change, mechanical energy. Whereas heat is a change in thermal energy. Okay, so if you walk over to a campfire and you're warming your hands around the campfire, it's very common for someone to say, oh man, I can feel the heat coming off of this. Well, actually, you don't feel heat coming off of it. You feel thermal energy coming off of it. The transfer of that thermal energy to you is a process called heat. Okay, so heat is actually not a thing, it's a process. It is the transfer of thermal energy. Okay, if I have a system and I want that system to have more energy, there's two ways to do that. I can do work on it. Okay, if I do work on it, then I'm going to add mechanical energy. And that might make the system move faster, okay, or move higher or something like that. Or I could put heat into the system, in which case I'm increasing the system's thermal energy and making it hotter. Okay, those are the two ways to increase the overall energy of a system. Do work or do heat. I know it sounds weird to say it that way, okay, but that's really what you're doing. Okay, you're either doing work or doing heat. Heat is transferring thermal energy to that system. Okay, so the energy of a system can be increased in two ways. Either heat can be added, okay, or work can be done. The opposite is also true. If a system does either one of these two things, that is heat or work, then it's going to lose energy. Okay, so if a system is transferring heat away from itself, it's going to have less energy than it had before. If a system does mechanical work on something, it's going to move slower than it did before. Okay, how many people have ever played pool before? Okay, so it's very much like when the cue ball hits something. Okay, the cue ball slows down, but the ball it hits speeds up. Okay, that's work. It's transferring its mechanical energy to the other ball. Right, so as a result, it slows down, the other ball speeds up. So it has less energy, the other ball has more energy. Okay, but the amount of total energy remains the same. Okay, especially if we take into account that you would have heard them hit. Sound is a form of energy. Okay, that's going into the surroundings, things like that. Okay. All right, so these are the two forms of, or transfers of energy. If I take like a heated up metal rod, and this is an example of what not to do with a hot metal rod. How's she holding on to it? Would you hold on to a hot metal rod with bare hands? It's not good. Not very smart. Okay. Anyway, she puts the hot metal rod in water. When you put something really, really hot in water, what happens? Yeah, it sizzles and steam goes everywhere, right? I'm transferring heat from that to the water. Okay? The water gets hotter, sometimes even changes state to a vapor, right? That's all evidence that energy has traveled or been transferred from the hot object to the colder object. Okay? If I compress a spring or stretch a rubber band like in a pogo stick, okay, or like a bungee cord, right, then I'm doing work. I'm transferring mechanical energy to that other object. So if I go bungee jumping, which I wouldn't do because I'm old and I have too much to live for. Okay, so if I go bungee jumping, okay, I jump off the cliff, and as the bungee cord stretches, I slow down, hopefully. Okay, now what's happening to the energy of the bungee cord? As I stretch it, the energy of the bungee cord is going to increase. Yeah, I'm putting a whole bunch of elastic potential energy into that bungee cord. Okay, as I stretch it, I lose energy, the bungee cord gains it, and then when I get to the lowest point, hopefully above the ground still, okay, I get thrown back up in the air because now the bungee cord will do work on me. It's going to give all my energy, well, not all of it, but most of my energy back to me and shoot me back up in the air. Okay, if you've ever watched somebody bungee jump, right, they oscillate kind of at the bottom, up and down as that process happens. Okay. So first law of thermodynamics is here. I think it's highlighted in your notes as well. Okay, but make sure you know that. Okay, it's a restatement of the law of conservation of energy. Okay, so it states that the total amount of energy, including heat, in a system and its surroundings remains constant. Energy can't be created, it can't be destroyed. Okay, whenever heat is added to it, it transforms into other forms of energy. Okay. When we talked about the types of energy, one of the examples was when Joseph Black, the guy who renamed himself Count Rumford, okay, the guy who did the cannons, he discovered that mechanical energy could be turned into thermal energy or heat, right? Because they could boil a kettle on top of those cannons while they were boring them out. Okay, so if I add mechanical energy to a system, it's not necessarily that all of that mechanical energy will go to the system. Some of it will be lost. Okay, it'll be lost to the surroundings as other forms of energy. Okay, can you hear a drill when it's grinding? Right, like it makes noise, right? Sound's a form of energy. That means that some of that mechanical energy I was trying to put in isn't going in. It's turning into sound. A lot of it's turning into heat. Okay, and some of it is actually doing useful work in changing the shape of whatever it is I'm drilling. Okay, and that's of course the desired outcome. So friction is a force that makes it look like energy doesn't get conserved because it steals energy away, and it results in that energy that I'm putting in being turned into less useful forms, heat, sound, okay, and things like that. Okay. Now, how many people have heard of a perpetual motion machine before? Okay, so a perpetual motion machine is first off purely theoretical. Okay, if we were able to build one, a perpetual motion machine would run continuously and would never require any energy to be put in. Right? It would just always run. But that would mean if I was watching this machine run, that, like, how would it look? Or like, what would my experience be if I'm watching a perpetual motion machine run? Okay, would it sound like a car engine? No. What would it sound like? Nothing. It would make no sound at all. Because if it made sound, it would be losing energy, and then it would stop. Okay? A perpetual motion machine can only run continuously because it never loses any energy. It's 100% efficient. Okay? Can never lose any energy. So even if we could build one, would it ever do any useful work? No, because work is a transfer of energy. If the machine did work, it would lose energy and stop. Okay, so even if you could build a perpetual motion machine, it would be nothing more than a scientific curiosity. It would be, other than kind of neat, totally useless. Because if it did any work, it would stop. Okay, you can't get something for nothing. Okay, I can't have this machine that I didn't put any energy into do any work. Because if it does work, it loses energy and it stops. Okay, that's why we constantly have to put fuel in cars and lawnmowers and things like that, or why electrical appliances always have to be plugged in. They're always doing work. They're transferring energy away, and they can't keep doing that without a supply of energy. Okay, everybody with me there? Yeah? Okay. All right, so that's to do with perpetual motion machines. So these are some of the ideas people had for perpetual motion machines. They thought maybe if they built this like pie wheel, that would run continuously, because they have these kind of arced, the pie pieces are kind of arced. So as the ball would fall to the edge here, it would push the outside of the circle downward, and that would drive the circle around. Okay, and then because these are arced, the ball would roll back to the middle. Okay, as the ball goes up, and then it would just run continuously. All done, Kayla? Done, or just have a question? Done. Okay, thanks. Just put it on my desk. So it's a nice idea, but if this thing's running, can I hear it? Yeah, I'm going to hear those little marbles or whatever they are moving around inside the pie pieces. Okay, I'm going to hear them hit the edges. I'm going to hear them roll. Okay, there's probably also friction here on this pivot point in the middle. Okay, so as a result, there's going to be energy lost at all those positions. Okay. This one I thought had potential. Okay, if I put a magnet at the top of this ramp and I have these metal balls, they would get drawn up the ramp by the magnet. And then they would fall through the hole at the top and then roll back down this other ramp. And they'd come back out through this little door. And there's the problem with that one. To open the door requires energy. Yeah. Okay. You would always lose a little bit of energy every time the door was open. Okay. Now, this wouldn't be a true perpetual motion machine because there is a source of input energy here in the magnet. Okay, will a magnet be magnetized forever? Magnets actually do demagnetize slowly over time. Okay, so again, you can't get something for nothing. All right, second law of thermodynamics. So we said the first law of thermodynamics says energy can't be created or destroyed. You can put energy in by doing work or heat. Okay, the second law of thermodynamics says which way energy flows. Okay? And energy always flows from a high energy object to a low energy object. Usually, the surroundings are lower in energy. Okay? See you later. Okay? So usually the surroundings are lower in energy, and that's going on right now. Okay? All of our bodies are around 37 degrees, but the air temperature in here is much lower than that. So energy naturally flows away from us. Okay? If you've ever been near somebody who has a fever, you can feel the heat coming off of them sometimes, right? Like, and that's of course how we check to see if somebody has a fever. I take my hand that's 37 degrees Celsius and I put it on their head. Okay? If their head feels warm, it's because they're transferring energy to me, because they're hotter than me. Okay, and so I can tell they're not healthy because their body temperature is higher. All right, so the second law of thermodynamics just tells us which direction does heat go. Heat always goes from the hot object to the cold object. You cannot transfer coldness. Okay, there's no way to transfer coldness. Being cold is a lack of energy, okay, not a excess of cold. Okay, you can't have an excess of cold. Everyone follow on that? Okay, so an ice cube makes a drink cold because it can absorb what? It can absorb heat. Okay, it's in a very low energy state. It's a solid. Okay, it's very low in temperature. As soon as I put it into a drink, the drink is the hotter object, and energy transfers to the ice. Okay, and that means the drink gets colder. Okay, not that the ice cube is transferring coldness; it's that the drink is actually transferring heat to the ice cube. Right? Eventually, when the ice cube melts, the drink will be warm again. Okay? You can only absorb so much. All right, so definitely, again, know the second law of thermodynamics. You got to know the two laws of thermodynamics for sure. All right, so this idea that heat goes from hot to cold, okay, led people to think if we can get something in between the hot object and the cold object, the heat flowing from hot to cold should be able to do some work for us. Okay? We should be able to harness that flow of energy as it goes and make it do useful work. Okay? And this is where the idea of the heat engine came about. Okay? We still use this idea to an extent, but it's not, the pure heat engine isn't really practical. Okay? So if I have this high temperature area and this low temperature area, heat's naturally going to go this way, but if I get something in the middle, I can maybe get that heat to do some work. Okay? Now, that means not all the energy goes to the low area, but some of it gets harnessed along the way. Okay? So the idea of the heat engine, okay, looked something like this. So we built this boat, and it would have this short pipe that only goes this far into the water, and there'd be this really long pipe that goes way down deep where the water is much colder. And the idea being that the heat from the hot water that's near the surface would go through the motor, through the turbine or the heat engine, okay, and then down through the pipe into the cold water. Does it work? It doesn't work. Okay, it's nice in theory, but it doesn't work. Okay, it works when you put it in a jet engine, but it doesn't work here in a boat. The reason it doesn't work here in the boat is, what's the water's motivation to go on this path when it can already mix with the hot and cold water here? Okay? It's like saying to me, there's two ways to get home. One way involves you only going this far and it's all flat, and the other way requires you to go 20 kilometers and it's all uphill and 3 feet of snow. Which way am I going to go? Right? I'm going to take the easy way. Okay? So this one doesn't really work because you can't get a huge temperature differential between the warm and the cold, and they're already in contact with each other. There's no reason for the water to follow this path. But it does work if you can make a huge difference between the hot side and the cold side. And that's what a jet engine does. Okay? A jet engine is just a turbine, okay? And on one side of the turbine is where the fuel is burned. That area is very hot because jet fuel is essentially just kerosene. Okay, which is what used to be used in like camp stoves and stuff. And then on the other side would be much lower temperature air, especially when you're at 30,000 feet, okay, where the cruising altitude of a jet, where the air temperature would be like -20. Okay, so the air flows very quickly through the turbine because we've got a hot spot and a cold spot. And energy is trying to go from one to the other. As it goes through, it turns the turbine. Okay, and when that turbine turns, it pulls air through, creating thrust. Okay, so the change in temperature, as long as the difference in temperature is really great, okay, then this works quite well. But as the temperatures get closer together, it doesn't work well at all. Okay. Okay, so heat engines, like we said, a jet engine is an example of a heat engine. Okay, an air conditioner and a refrigerator are an example of a heat pump. Okay, so heat engines do this. They convert heat into mechanical energy. Okay? Heat pumps use mechanical energy to transfer heat. Right? So we just said that the second law of thermodynamics says heat flows naturally from hot to cold. But a heat pump, like your fridge, is pumping heat from your fridge, which is cold, into your house, which is hotter. So it's going against that second law. A heat pump is like active transport, but for energy instead of materials. It uses energy to pump stuff in the wrong direction, okay? Or not so much the wrong direction, but the opposite of the natural direction. Okay? How many people have ever been next to their fridge when it fires up and you can feel the hot air blowing out from underneath it? Okay? If you've never done that, the next time it turns on, go stand next to it. Okay? You can feel hot air coming out from underneath because what's happening is inside the fridge, okay, inside the fridge is coolant. Okay? It's called a refrigerant. That's where a refrigerator comes from. Okay, and it goes through these little coils. You can actually, if you ever like pulled a fridge out, you can see the coils on the back. Okay, so the coolant runs through those coils and it absorbs energy from the food in the fridge. Now, when it does that, it changes state from a liquid to a gas. Okay, it takes a lot of energy to change something from a liquid to a gas. Okay, so it absorbs the heat from the food, changes state, and then is pumped to the compressor. Let me just put it on my desk. Okay, the compressor then puts pressure on this gas and turns it back into a liquid. And when it turns back into a liquid, all the heat it had absorbed is released. And then there's a little fan on the bottom of your fridge that blows that heat out into the room instead of back into the fridge. Right? This is why you can't use your fridge as an air conditioner. Homer Simpson once tried it. Okay? But you can't use your fridge as an air conditioner. Right? What he did is, well, his words to Marge were, I went downstairs to get something to eat and I opened the fridge and I noticed it was cold inside. Because that's how smart Homer is. Okay? So he said, what I did is I left the door open and I put a blanket over it. So he had this like tent that he had made, okay, that kind of enclosed the whole front. Well, here's the heat that's being pumped from the fridge into the room, except when you make a tent out of it, where's all the heat going? Into the area you're trying to cool. So the fridge just runs continuously until the compressor burns out, which is exactly what happened to Homer. He wrecked his fridge, okay, doing that. You can't pump the heat from the area you're trying to cool back into the area you're trying to cool. You'll never win, okay? You're just constantly doing work, right? If you have an air conditioner at home, it pumps the hot air outside, okay? So it cools the air inside and it pumps the heat out into the hotter area because it's usually hotter outside. All right, so with a heat engine, okay, obviously, like we said, we're following the second law of thermodynamics in a heat engine, okay? The simplest heat engine, okay, is something that doesn't look like this. You got like 90 degrees Celsius water and 10 degrees Celsius water. Obviously, heat, this is hotter, so the heat is essentially converted into other forms of energy and turns this fan. How long will this fan turn for? It'll only turn as long as there's... Right, as long as these two have some difference in temperature. Once these are the same temperature, then the fan won't turn. In fact, the fan will turn slower and slower and slower as these get closer and closer to the same temperature. Okay, so like we said, a heat engine follows the second law of thermodynamics. Okay, and it converts heat into mechanical energy. Okay. Yep. Yeah, a steam engine, well, and there's several energy conversions in a heat engine, or sorry, in a steam engine. First, you have the chemical energy turning into heat, and whatever you're burning, coal probably, right? And then that heat changes the state of water, so there's another energy change. And then the water's, the steam turns a turbine, so we're turning the essentially potential energy into kinetic by turning the turbine, and so on and so on, right? If it's a steam turbine, if it's like a steam piston, it's different then. Question? No. Okay. All right, and then like we said, for the heat pump, okay, the process is not natural for a heat pump. Like we said, it's kind of like active transport, so it requires energy, okay, in order to pump all of that energy away, okay, to pump it into the hotter area. Okay, I would like you guys to answer the circled questions.